Download this code from codegive.com, link in the description below. Don't chase test coverage, a practical guide to meaningful testing. Test coverage, measured as a percentage of your code base that's exercised by tests, is a common metric. It's easy to quantify and report, making it an attractive target. However, blindly chasing high test coverage can be counterproductive, leading to brittle, unhelpful tests that don't actually improve code quality. This tutorial explains why focusing solely on coverage is a bad idea and offers a more nuanced, effective approach to testing, illustrated with code examples in Python, but the principles apply to any language. Why simply chasing coverage is a bad idea. 1. Coverage doesn't guarantee quality. A 100% coverage score can still hide serious bugs. Consider this. A test like this achieves 100% line coverage. This test runs every line of the calculate_discount function. However, it doesn't reveal the crucial addition bug. The code works correctly only when the discount is 0, and the test only covers that one case. Coverage doesn't equal correctness. 2. Leads to trivial and brittle tests. The pressure to increase coverage often results in tests that simply execute code paths without asserting anything meaningful about the behavior. These tests are trivial. They verify obvious things that are unlikely to break, example testing getter/setter methods directly. Brittle. They are tightly coupled to the implementation details of the code. Even small refactorings can break these tests, requiring you to rewrite them constantly, wasting time and effort. This discourages necessary refactoring. 3. Encourages testing implementation details. Good tests focus on the what, the expected behavior, and not the how, the implementation. Chasing coverage often leads to testing private methods, internal variables, or specific control flow mechanisms. This violates the principle of black box testing, making tests fragile and less valuable. 4. Can mask real issues. By focusing on the easy wins in coverage, you might neglect the more complex and critical areas of your application that require deeper, more thoughtful testing. You might end up with high coverage in less important modules while leaving the core logic relatively untested. 5. Discourages refactoring and design improvement. When tests are tightly coupled to implementation details, refactoring becomes a much more daunting task. You become afraid to change the code because you know it will break the tests, even if the refactoring would improve the overall design and maintainability. This can lead to technical debt accumulating over time. A better approach: prioritizing meaningful tests. Instead of obsessing over a percentage, focus on writing tests that 1. Verify business logic and core functionality. Start with the most important aspects of your application. What are the critical features that must work correctly for the system to be useful? Prioritize testing these areas. Example: updated discount calculation. Good tests. These tests cover a range of inputs and edge cases, providing much more confidence in the correctness of the function. 2. Focus on behavior, not implementation. Test the observable behavior of your code. Treat your code as a black box, give it inputs and verify that it produces the expected outputs. Avoid testing internal variables or private methods directly. If you find yourself needing to test implementation details, it's often a sign that your code needs refactoring to be more testable. 3. Cover edge cases and boundary conditions. Pay special attention to edge cases, boundary conditions, and invalid inputs. These are often where bugs hide. Examples: empty lists or strings. Zero values. Maximum/minimum values. Invalid data types. Null/none values. 4. Use different testing strategies. Don't rely solely on unit tests. Consider other testing strategies, such as integration tests. Verify that different components of your system work together correctly. End-to-end tests. Simulate a user's interaction with your application from start to finish. Property-based testing. Define properties that your code should satisfy and automatically generate test cases to verify those properties. See example later. Fuzzing. Providing invalid, unexpected, or random data as inputs to a program. 5. Write maintainable tests. Follow these guidelines for writing maintainable tests. Descriptive test names. Use clear, descriptive names that explain what each test is verifying. Example: test calculate discount valid discount instead of just test discount. Arrange assert, AAA, pattern. Structure your tests using the arrange assert pattern. Arrange set up the test data and preconditions. Act execute the code being tested. Assert verify that the expected result occurred. Avoid duplication. Use helper functions or test fixtures to avoid duplicating code in your tests. Keep tests small and focused. Each test should verify a single, specific behavior. 6. Test-driven development, TDD. Consider writing tests before you write the actual code. This can help you clarify your requirements, design a better API, and ensure that your code is testable from the start. Code examples, illustrating the principles. Let's explore some code examples to illustrate how to write meaningful tests. Example 1, a simple queue implementation. Bad tests, coverage chasing. These tests are brittle and don't provide much value. If you change the internal representation of the queue, example using a linked list instead of a list, these tests will break, even if the queue still functions correctly. Good tests, behavior focused. These tests focus on the behavior of the queue. They verify that items are added and removed correctly, that errors are raised when appropriate, and that the peek and is_empty methods work as expected. They are less tightly coupled to the internal implementation. If you refactor the queue class to use a different data structure, these tests are less likely to break. Example 2, property-based testing with hypothesis. The hypothesis library is a powerful tool for property-based testing. It allows you to define properties that your code should satisfy and then automatically generate test cases to verify those properties. This single test, using the hypothesis library, effectively tests the fundamental FIFO, first in, first out, property of the queue for any list of integers. Hypothesis will automatically generate many different lists, including empty lists, lists with duplicates, lists with very large numbers, etc., to try and find any cases where the property is violated. This is far more comprehensive than writing individual unit tests for specific lists. Key takeaways. Focus on business value. Prioritize testing the core logic and features that are most important to your application. Test behavior, not implementation. Treat your code as a black box and focus on verifying the expected outputs for given inputs. Cover edge cases and boundary conditions. Pay special attention to potential error scenarios and extreme values. Use a variety of testing techniques. Don't rely solely on unit tests. Write maintainable tests. Use descriptive names, follow the arrange assert pattern, and avoid duplication. Use coverage as a guide, not a goal. Coverage metrics can be helpful for identifying areas of your code that are completely untested, but don't let them drive your testing strategy. Aim for meaningful tests, not just high coverage. Refactor towards testability. If a part of your code is extremely difficult to test, that's often a sign that it needs to be redesigned. Strive to write code that is modular, loosely coupled, and easy to test. By following these principles, you can create a robust and valuable test suite that helps you improve code quality, reduce bugs, and increase confidence in your application. Remember, the goal of testing is not to achieve a high coverage score, it's to ensure that your code works correctly and reliably.